today we should talk about section 3.6, zeros of polynomial functions. On the last lecture, we talked about division of polynomials, and I show you this special method called synthetic division, right? Synthetic division. Turns out this method is very useful. Today, it will allow us to do, for example, evaluation of polynomials, and we will be able to do that efficiently, right? Efficiently using this synthetic division. I will show you how. Mathematicians figure this out by discovering this theorem. Is called the remainder theorem, okay? And what does this theorem say? Well, it says that if you let k be some real number, positive or negative, if a polynomial f of x is divided by x minus k, using these methods in this synthetic division, right? Then the remainder is the value f of k. Okay, so what does this tell us? Well, it tells us that, let's say I want to compute f of k, since it's equivalent to divide the polynomial by x minus k, and this is good for synthetic division, right? As a divisor, I can use synthetic division to do this evaluation, right? Yeah, that's the idea. Let me show this to you with an example here. So example one here says, use the remainder theorem, this theorem, right? To evaluate f of x equal x cubed plus x squared minus 3x plus 7 at x equal 2. At x equal 2. Okay, let's do that. Let's do that using synthetic division. So the theorem says that in order to do this evaluation at x equal 2, it is equivalent to divide this polynomial, right? X cubed plus x squared minus 3x plus 7 by this binomial x minus 2. Notice the relationship. 2 here, over here, I'm writing opposite, right, of this. Right? X2 minus 2 here. All right, so let's divide then this polynomial by x minus 2. And you will see that in the end, we will be able to get the evaluation, which is what we're looking for, right? F of 2 is what we're looking for. All right, so if we pick up the coefficients, there is an invisible one here, another invisible one here, minus 3 following 7, right? These are the coefficients of the dividend. Now for the divisor, remember, we took the opposite of this, right? Opposite of this, opposite. But notice, if I take the opposite of the opposite that I already took, I come back to this number 2, right? You see it, guys? So opposite, same as this, right? You can just take this number and put it in here because of this transition, right? Very good. Now, let's do the synthetic division, right? Remember, it always starts by bringing the first number down as it is, 1. Then you multiply these two numbers, 1 times 2, 2. Then you add these two guys, right? 1 plus 2, that is a 3. You multiply again, 3 times 2, 6. 6, you write it below this third coefficient, and then you add. Minus 3 plus 6 is just 3, right? 3 times 2, 6, right? 6. And finally, adding 7 plus 6, that is a 13, right? That is a 13. We separate this 13 from the rest. We know this is the remainder of this division. But now, since the remainder, there is 13, according to the theorem, also that is the evaluation, right? The evaluation of the polynomial at x equal 2. That is the important part, a big deal here. Then we can say, based on this theorem, right? The evaluation of my function f at x equal 2 is equal to 13. Professor, the evaluation equal to 13. Well, guys, you can always check, right? You can always check. If you bring up your calculator, we're gonna evaluate this directly, right? Directly and see, right? So it should be 2 cubed plus 2 squared minus 3 times 2, right? Times 2 plus 7, indeed 13, right? You see it? It works. But you will say, Professor, what's the big deal of doing this way compared to doing this directly? Well, guys, notice that I explained to you, right? If you do it this way, since you are using synthetic division, you are doing this efficiently. Synthetic division is an optimal algorithm, right? We are only using here basically 3 multiplications, 3 additions. Compared to this computational speaking, you have to use 3 multiplications here, 2 more multiplications here, I think 3 or 4 additions. So this method is optimal. That's the idea. Okay, it's going to help us also with more stuff that is coming up. Okay, guys, so now I want you to practice, right? Remember, one more thing before we go into practice. This guy, if you want to go directly to here, is the same, right? Because opposite here, but opposite of the opposite is the same, right? It's the same. So very good, very good. So let's practice. So can you try this one now? Let me show you one example. Let's see number 3. This one. Can you try this? A little bit tricky, because instead of my 2 is now -2, but we should be able to do it, right? I'm gonna give you the hint. Divide 3x cubed minus 7x squared minus 3x plus 3 by x plus 2, right? Remember, -2 here, opposite here. But in reality, when you work here with the synthetic division, on the corner is just the same, right? Because opposite of this, again, -2. So do that. And use for the coefficients 3, -7, -3, and 3, right? Yeah, and figure out the remainder. That should be the evaluation. Welcome. I think Heilun Chen just joined. Welcome. We just started with this topic. It's called finding the zeros of a polynomial. We're using synthetic division first to evaluate the polynomial, right? So the question here was evaluate f at -2. Yeah, that's the idea. Using synthetic division, right? Synthetic division. I see some activity on the chat room. Let's check. Gabriela, very good. Excellent. You got it. Yeah, very good. Excellent. Very good. Yeah, let's do it together, and then I will give you another one, okay? So it's important, this method. So we start by bringing down the first coefficient as it is a number 3, then 3 times -2, multiply, that is a -6. Add these two numbers, -7 plus -6, that is a -13, right? -13 times -2, negative and negative positive, 13 times 2, 26, right? 26 plus -3, 23, right? 23 times -2, -46, right? -46. And adding these two, finally, 3 plus -46, is negative 43. If the numbers get really big and they're not friendly anymore, you may use your calculator, your decimal scientific calculator, any scientific calculator you have to add these numbers, right? But what is true is that you will get, no matter how you do it, this as your remainder, right? Minus 43, remainder. Remainder is negative 43. But mathematicians shown that this is also the evaluation of this polynomial f at this guy, minus 2, right? Same. So therefore, very good. This should be the answer, right? We use synthetic division to do the evaluation. Okay, now guys, try this one, number 5. Okay, it's the numbers are a little bit big, but I think using your calculator you can help yourself out if needed. And notice the degree of the polynomial is bigger, and you will really appreciate this method here because doing it directly probably much harder. All right, so as usual, the hint should be you're supposed to use synthetic division. You're supposed to, since you're looking for f of 2, you're gonna divide this guy, right? This guy by x. This is 2. You here write the opposite, minus 2, right? But when you go back to the corners, it's you're taking the opposite, negative 2, it's still 2, right? Same. Huh? And for the coefficients, we know that we will have 9, 10, 6, negative 6, and 16, right? 16. Yeah, go ahead. Yeah, do the synthetic division, get the remainder, and that turns out to be the evaluation, right? The evaluation. Yeah, and as usual, guys, if you have questions or any comments, let me know. Yeah, and as an extra hint, remember it all starts the synthetic division by bringing this down, right? As it is, it's a 9. Then 9 times 2, 18, and then you add and you continue, right? You continue there. Yeah, the numbers I see they're not that small, but if needed, use your scientific calculator. Let's see. Okay, so let's do this together, right? Together. Let's do it together. Yeah, and if you finish, just let me know. Okay, so 9 comes down as it is. 9 times 2 is 18. 18 plus 10, 18 plus 10, 28, right? 28. 28 times 2 is 56, right? Adding 56 plus 6 is 62. 62 times 2. It's a big number. Then 2 times 2 is 4. 6 times 2, 12. 124, right? 124. 124 minus 6. 118. Yeah, I see the numbers are big. Now, 2 times 118. Again, if the numbers are too big, just use your calculator here. 2 times 118. That is 236, right? 236 is right here. 236. And finally, I have to add these two guys. Adding these two guys. 16 plus 236 is 12. Carry 1. This is a 5 and 2. The last number must be separated from the rest. That is the remainder, right? Remainder of this division is 252. But mathematicians have proven that this is also the evaluation of this polynomial function at the real number 2, f of 2. That's the same. Okay? So you can see, there we go, right? Very good, guys. Yeah, try to remember this for your homework. They will ask you questions related to this part. And remember, if some terms are missing, you are supposed to put zeros there, right? Zeros, and complete the polynomial before you do your division. All right. Now, let's continue with another application of synthetic division. It turns out another useful thing that you can do using synthetic division is this. You can identify if a binomial is a factor of the polynomial, the given polynomial. So we can use synthetic division to find binomial divisors of polynomial, binomial divisors or binomial factors. Mathematicians discovered this theorem. They call it the factor theorem. K is a zero of f of x if and only if x minus k is a factor of f of x. So somehow, if you want to check if f minus k is a factor of f of x, all we gotta do is this. We gotta see if k is a zero of f of x. But for k to be a zero of f of x, then when you evaluate k at f of x, you should get 0, right? 0, which is equivalent to say, because of the remainder theorem, that the remainder should be 0, right? So if the remainder in our synthetic division gives us 0, it means that we got ourselves a binomial factor like this, okay? I will explain that to you. All right, so let's explain this with this example. Here it says, show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. It means that this binomial divides this polynomial evenly, right? Exactly, no remainder. Find the remaining factors and use the factors to determine the zeros of the polynomial. All right, so let's do that together, okay? So we can use synthetic division to show that x plus 2 is a factor of the polynomial. How? Let's do the synthetic division, right? Remember here, there is an invisible one. So we're going to start by considering that on the top row of the synthetic division, right? This is going to be my synthetic division. 1 here, minus 6 here, minus 1 here, another invisible one, right? 30 here, right? 30 here. Good. Now, what goes in this corner? Anyone in the chat could tell me what goes in this corner. Notice that we are dividing by x plus 2. Gabriela, excellent, excellent. You made my day. Minus 2, right? Opposite again, right? Always the relationship between the factor form and what you put here, opposite, right? When you are evaluating, it's a different story. We said that it ended up being the same, but for this, opposite, minus 2 there. Excellent. Now, let's do the synthetic division, right? Bring down the first number as it is, this guy, 1, right? 1 times negative 2, negative 2. Add these two guys, negative 6 plus negative 2 is a negative 8. Multiply negative 8 times negative 2, that is a positive 16. Adding these two, I get 15 here. 15 times negative 2, negative 30. A special number for us because 30 plus negative 30, 0, right? 0. This division is exact, remainder 0. Remainder 0. 0 means division is exact. Division is exact, right? And not only that, then we can claim that then this x plus 2, the divisor, this guy, is a factor, right? Is a factor of the polynomial x cubed minus 6x squared minus x plus 30, right? Is a factor. It's a divisor. So now they say, right, using this information, find the remaining factors, the other factors, right, of the polynomial. Okay, so that shouldn't be difficult because notice when a division is exact, the dividend is equal to the divisor times the quotient, right? Quotient times the divisor. But what is the quotient here? From here, I can extract it. This one tells me that this should be, let's write here, quotient equal 1x squared minus 8x, remember, plus 15, and remainder 0, right? This is the quotient extracted from here, right? But that goes here, look, x squared, we don't have to write the one up front, minus 8x plus 15, quotient, multiply by divisor, but the divisor was x plus 2, right? Maybe I can write this for you to see this. This is always a fact, right? When a division is exact, the dividend is equal to the quotient times the divisor. It's like if you divide 12 by 4, it's 3. 3 times 4 has to be 12, right? So like that. All right, great. But now they want all the factors, right? All the factors of this polynomial. So we continue the factorization. Factor. If you factor this should be x here, x here. I need two numbers whose multiplication is 15, whose sum is -8. After some trial and error, you will figure out that those numbers are 3 and 5. But since you want the sum to be -8, this has to be negative, this has to be negative, right? Now, guys, look, I was able to factor this completely, this polynomial, right? With the help of synthetic division here. This was factored further. When you get these 3 binomial factors, then mathematicians call this full factorization. You cannot factor anymore, right? Full factorization. Now, Professor, what's the big deal of getting the full factorization? Well, the big deal is this: to find the zeros of the polynomial. If you have the full factorization, you simply set the polynomial equal to 0. This is our polynomial, right? In factor form. So we're gonna set that equal to 0. And from there, you will see that it will be really, really easy to pick up all the zeros of this polynomial. Look, after you set the polynomial equal to 0, you set each factor containing the variable equal to 0, right? And from there, you will see the zeros. X equal 5 is 1 0. X equal 3 is another 0, right? Adding 3 to both sides. Subtracting 2 to both sides of this equation. X equal -2 is the other 0. 3 0, right? So the zeros, the zeros of the polynomial are and you may list them, right? -5, 3, and -2, right? In any order. These are the three zeros, right? As you can see, using synthetic division, we were able to figure out that this was a factor. Then further, we factor this. We got the full factorization. And after that, we set everything to 0, and that's it. Yeah. Yeah, this one is positive. Very good, very good. Nice catch there. Yeah, this one is positive. Yeah, true. Right? 5, 5. Yeah, notice the relationship, right? On the factorization -5, on the solution 5, opposite. On the factorization -3, on the solution on the 0, 3. On the factorization +2, on the solution on the 0, -2, right? You see the relationship? Try to see that, because on the homework, they're going to ask you this type of questions. They will ask you to write the polynomial in factor form, having the solution. So go back by taking the opposites, right? That will help. Yeah, very good, guys. Excellent, excellent. Okay, now let's go over exercises, right? Let's go back to the worksheet and let's see an exercise that would clarify this part. So let's try now. I think this one is a good one. Number 8. They say use synthetic division, okay? Use synthetic division to divide this polynomial by x plus 5 and use the result to find all the zeros of f, right? All the zeros of f. So let's try to do what I just did on the example, right? And as a hint, as usual, I will give you something. As a hint, start with this synthetic division. Look, this is invisible 1, right? So 1 here, 12, next coefficient 41, next coefficient 30, right? And who can tell me what is gonna be placed on this corner? Anyone? The chat or verbally? I see on the chat. Yeah, very good, guys. The relationship, -5. Excellent, Gabriela. Yeah, excellent. -5 here, right? -5, because it's the opposite, right? That's the relationship between what appears on the factor form and what you should write in this corner. All right, -5, 1 here, and continue, right? Multiply these two, -5, add, and continue this. Finish this, and from there, you will get that this guy is a divisor, but also it will allow you to get the full factorization, right? And from the full factorization, I think we can find all the zeros, right? All the zeros. Yeah, go ahead, guys. So try to do this. So, and then I will ask you to probably number 8. Yeah, try, guys. Finish the synthetic division, then we go from there to a factorization. And after that, you pick up the zeros of the polynomial, right? Yeah. Yeah, if the numbers are not friendly, you may use your calculator. Yeah, very good. Let's see for number 7. Very good, Gabriela. Excellent, excellent. Yeah, very good job. Excellent work. Yeah. We start, as suggested here, by dividing the polynomial by x plus 5 by placing minus 5 here. 1 comes down as it is. 1 times -5, -5. Adding -5 plus 12. That is just a 7. 7 times -5, -35, right? Adding these two. That is just 6. 6 times -5, -30, which is a good number for us because when you add 30 to its opposite, -30, we get 0 here, right? 0. It means that this is a factor. This is the quotient. Remember, quotient. 1 times x squared plus 7 times x. Notice these are the coefficients of the quotient, right? Plus the constant term 6. No remainder. But since the division is exact, I can say that the polynomial, this guy, right? This big polynomial is in factor form, and that's what is important here. In factor form, according to the factor theorem, is this. Quotient x squared plus 7x plus 6 times divisor x plus 5, right? X plus 5. Great. Now, I continue the factorization here. To factor this type of polynomials is easy. You learned this in previous courses, right? You just kind of do the FOIL method backwards. You look for two numbers whose multiplication is 6, whose sum is 7. After some trial and error, you will get that those numbers are 6 and 1, right? Positive both. 6 plus 1, 7, right? And then finally, we set the polynomial, right? F of x, which is this, right? Equal to 0. But that just means that x plus 1 times x plus 6 times x plus 5, which is the polynomial in factor form, is just equal to 0, right? From there, setting each of these equal to 0, we will end up with the opposites of these numbers, right? For our solutions, right? For our solutions, the opposites, right? Subtracting 1 in both sides, x equal -1, one solution. Subtracting 6 in both sides, x equal -6, second solution. Then from here, x equal -5 is the last solution, right? So the three together, -1, -6, -5, right? And this is this guy. Excellent, excellent. Very good. Yeah, very good. Excellent, excellent work. Can you try now this one, number 8? Yeah, I will leave this for you to follow the method, right? And as usual, the hint should be this, right? Here, we're gonna use invisible one here, another one there that they wrote for some reason, -26, 24. And at this corner, as usual, right? At this corner, as usual, we're gonna write the opposite of this guy, -6. Very good, very good. Okay, so start there, bring this down as it is and multiply -6 and continue, right? Continue there. Yeah, make sure that you will get as a remainder 0 because the division should be exact, right? For that, for this to be the divisor, right? And then get from there your solutions or your zeros. Very good, guys. Very good. Yeah, try, give it a shot. And then we will go over the other forms. Okay, number 8. I see some activity in the chat room. Yeah, it's a very nice method, this synthetic division. Gabriela, excellent, excellent. Excellent, very good, good job, right? Yeah, you got it. Yeah, so 1 comes down, 1 times -6, -6, -6 plus 1, since this is the dominant in value, is -5, right? Gives the sign to the result. Now, -5 times -6, negative and negative positive, 5 times 6, 30, right? 30 here. And then adding -26 plus 30, that is a 4. 4 times -6, -24, right? Which is a good number for us because 24 plus -4 gives us 0 here, 0. Remainder 0, which means that the division is exact and this x plus 6 is a factor. It's a factor. Right away from here, retrieve your quotient this way, right? Plus 4, this is the quotient. And since the remainder is 0, this polynomial x cubed plus 1x squared minus 26x plus 24 in factor form is the quotient x squared minus 5x plus 4 multiplied by the divisor x plus 6, right? We factor this further, right? Using a method that you learned before, right, in previous courses. We need two numbers whose multiplication is 4, whose sum is -5. Those numbers are 4 and 1, both negative, right? Both negative because the sum needs to be -5. Great. This is a full factorization. From there, you just set your polynomial equal to 0. From there, we will get that all this equal to 0. And from there, we will just take the opposites of these guys, these numbers that appear on the factorization, right? And these guys, these numbers will give us the zeros of our polynomial, right? X equal 1 from here, X equal 4 from here, right? And X equal -6 from here, right? These are the 3, 1, 4, and -6. Excellent. Don't worry about the order in which they appear within braces. As long as they are all there, that's the one that you have to take. 1, 4, and -6. Very good, very good. Now, sometimes they're going to try to trick you with a different form. I will explain, right? I will give you an example and then I will ask you to do one. For example, what about this? Instead of giving you the divisor in factor form, they just say this, right? Use synthetic division to show that the number given to the right, this number, right, of the equation is a solution of the equation, a zero of the polynomial, right? Then solve the polynomial equation. All right. So in this case, they are giving me some hint, right? They are saying that this guy somehow, x squared plus 2x plus 8 is divisible by x minus 2, right? X minus 2. How do you know, Professor? Well, because they are saying that this is a 0. Divisible by x, I take the opposite, right? Minus 2 is divisible by this x minus 2, right? So this is what they are saying here. So I'm going to use that information and go ahead and do my synthetic division with invisible one here. -5, 2, 8. And at this corner, I'm supposed to put the opposite, right? But the opposite of the opposite is the number itself, 2, right? 2. So if they give you this alone, it's equivalent to take just this, the same, right? 2 here. And go ahead with the synthetic division. 1 down here, 1 times 2, 2. 2 plus -5 is -3. -3 times 2 is -6. Add 2 plus -6 is -4. negative 4 times 2 is negative 8. Good number for us because 8 plus negative 8, 0, right? Confirms that the division is exact. Gives us the quotient, which is going to be 1x squared. I don't have to write the 1, but let's just write it for explanation. Minus 3 times x minus 4, right? This is how you retrieve the coefficients of your quotient. This is your quotient. But now, since the division is exact, right? It's exact. This is a divisor of this guy, a factor. Then one thing you can do is this. This polynomial can be factored as this. This polynomial is this. Quotient, right? Multiply by your divisor, this x minus 2, right? Great. Now, further, we can factor this quadratic polynomial, right? It's easy to factor using previous knowledge that we gained in previous courses. So two numbers whose multiplication is negative 4, whose sum is negative 3. After some trial and error, you will get to see that those numbers are minus 4 and plus 1 because you want the sum. Minus 4 plus 1 is negative 3, right? Great. This is the polynomial. Now you set your polynomial to be equal to 0, which just means this. And from there, you will pick up your zeros, your solution, right? X plus 1 equals 0 leads to x equal negative 1, first solution. X minus 4 equals 0 leads to, adding 4 to both sides of the equation, x equals 4. And x minus 2 equals 0 leads to x equal 2, right? I want you to recall this relationship. Look, on the factorization, plus 1. On the solution, minus 1. On the factorization, negative 4. On the solution, opposite 4. On the factorization, negative 2. On the solution, positive 2, right? Opposite. Very good. So can you try this one? Now when you're on, and then we will move on. Yeah, we're going to talk about the other theorem, the other two worksheets. Can you try this? I will leave this for you to check. Yeah, try to do this. A little bit tricky there, but I think you will handle this. Find all the solutions, right? Using synthetic division. Yeah, maybe I should give you a hint. If this is true, then the polynomial 2x cubed plus 10x squared minus 4x minus 48 is divisible by x. Notice this is minus 3, right? So you gotta write the opposite here, plus 3. Opposite. Right? Yep, but then when you do the synthetic division, opposite of the opposite is the same number, right? So since you are taking the opposite again of this becomes again minus 3, which turns out to be the same, right? Same here. If you want to go straight from here to here, same. Yeah, here was opposite, but this is same. Very good, guys. So do that. Yeah, so we have 210 minus 4 minus 48. And do the synthetic division, right? By bringing this down as usual, 2 times 3 minus 6 and continue there. Add, multiply again, add. And you're supposed to make sure you get 0 on the corner, right? At this corner here for the remainder. Yeah, and the question that you don't see there is what's this? Find all zeros of this guy, right? Or solutions, because they show equation, right? Solutions. Let's write it here better. All solutions of that equation. Mm. Okay, guys, so let's go over this together so we can take our break. Yeah, if you finish, just let me know. So if we bring this number 2 down as it is, 2 times -3, -6, adding -6 plus 10, that is a 4. I see. Gabriela, excellent. Very good. Excellent. You got it. Yeah, very good. Great, great, great. Excellent. Okay, great. So 4 here times -3 is a -12. -12, right? And -12 added to -4, -12 plus -4 is -16. Now, -16 times -3, negative times negative, positive, positive, and 16 times 3, 48, 48, right? 48, this is gonna be 0, good for us, 0. Which means that the division is exact, and moreover, the quotient of that division can be retrieved from this set of numbers. Quotient is equal to 2x squared plus 4x minus 16, right? That's the quotient. And also, since the division was exact, according to the factor theorem, we can say that this polynomial, this cubic polynomial, right? In factor form can be written this way. This guy, the quotient, right? The quotient 2x squared plus 4x minus 16 times the divisor, but the divisor was x plus 3, right? X plus 3. And further, we can factor this, right? It's tricky. Yeah, but I can factor out 2 first, the greatest common factor. 2 into 2x squared is just x squared, plus 2 into 4x, 2x, minus 2 into 16, 8, right? 8. Yeah, tricky polynomial to factor. And now we can use the FOIL method backwards, right? Yes. X. In our previous knowledge, we look for 2 numbers whose multiplication is -8, whose sum is 2. After some trial and error, you will discover that those numbers are 4 and 2. But since I want the sum to be +2, this should be negative, this should be positive, right? Very good. Now, this is the polynomial in factor form. Next step is set. Well, it's already set equal to 0, right? To say that this is equal to 0, we should write it differently here because there's no functional notation here, but to say that this guy is equal to 0 is equivalent than to say that this in factor form, right, is equal to 0, right? Because they are the same, right? This is this guy. All right, but now setting each of the factors containing the variable equal to 0, we should be able to get our solutions, right? Yeah, plus 3 here. Sometimes when I do this, students say, Professor, but you forgot the 2. What about the 2? Don't worry about these 2. The factors that are important are the ones containing the variable, because notice if you divide by 2 both sides of this equation, disappears. 2 into 2 is 1, 2 into 0, 0, right? So really, this is enough. Plus 2 will give you 2 opposite of negative 2 as your first solution. Subtracting 4 in both sides, x equal minus 4. This is your second solution. Subtracting 3 in both sides, x equal negative 3. That is your third solution, right? So these are the 3 solutions that you have to look for. Excellent. Look, 2, minus 4, and negative 3 in any order, as long as they are all there. This is the one you have to choose, right? Very good. Very good. Answer was A. Excellent. Very good, guys. So now let's talk about the rational zero theorem. In mathematics, this word rational means just fractional form, right? Any number that can be written as a fraction is called a rational number, right? 2/3, 1/5, 7/2. Even the whole numbers, 3, 4, they can be considered to be rational number, because 3, 4 can be written as 3/1, 4/1, right? As fractions, so rational number. Now, mathematicians discovered that if you have a polynomial having integer coefficients, right? These guys, coefficients are all positive or negative whole numbers. Then every rational zero, right? Meaning every fractional zero, right? Of f of x has the form p over q, where p is a factor of the constant term a0, the last number that appears here on the polynomial, and q is a factor of the leading coefficient a sub n. So important here, the constant term, and this included sign, right? This guy, and this term, the leading coefficient, these two. The ones in the middle, not so important, but for P, we're going to look at factors of this guy. For Q, factors of this guy, okay? Let me show you an example. Suppose they ask you to list all possible, this word important, okay? Possible, all possible rational zeros of this guy. Not the rational zero necessarily, right? Possible, they say possible. Applying the theorem. This is the polynomial. In order to answer this question, you simply look at the last term is called a constant term, right? Plus 6 in this case. And the first term, in this case, nothing here, but there is always an invisible 1 there, right? 1. And you go like this. You will say possible rational zeros. Possible rational zeros, fractional zeros, right? Are going to be equal to this. They will be determined by this fraction. Factors or divisors, right, of 6, this guy, 6, divided by factors of 1. Why 1? Because of this guy. Maybe I can highlight this so you can make the connections in your mind, that this with this with this. Okay, great. Now, next you do the following. You say, okay, what are the factors of 6? The factors of 6 are, you start with the number 1. 1, of course, is factor of any number, because 1 goes into any number evenly, right? So plus minus 1. You start with this, plus and minus 1, both. Next factor of 6. The number 2 goes into 6, right? So plus minus 2. Next factor of 6. The number 3 goes into 6 evenly, right? So plus minus 3. What about 4? 4 doesn't go evenly into 6, right? Doesn't go exactly into 6, so it's not a factor. 5 is not a factor. 6 6 is a factor. 6 goes into 6 once evenly, so plus minus 6. It starts with plus minus 1, ends with plus minus the number, plus minus 6 in this case, okay? That's this. This is the factors of 6. What about the factors of 1? Well, 1 has just one factor, itself 1, right? So I'm going to write here plus minus 1. Okay, great. So now for the identification of possible rational zeros, you just do this. Plus minus 1 into plus minus 1. What's that? Well, that is just plus minus 1, right? Plus minus 1 into plus minus 2. Well, that's just plus minus 2, right? Let's just put this in this column. All right, next, plus minus 1 into plus minus 3. 1 into 3 is 3, so plus minus 3. And plus minus 1 into plus minus 6, plus minus 6, right? Done. This is the list of possible rational zeros, okay, for this particular polynomial function, right? If you look for zeros and you're looking for rational zeros, these are the ones that you have to think of, right? Very good. Another example, a little bit more challenging. What if they give you this other polynomial, 2x to the 4 minus 5x cubed plus x squared minus 4, and they ask you to find all possible rational zeros of this polynomial? Well, again, we pay attention to the last number, which is called the constant term, and we pay attention to the first number that is called the leading coefficient, 2 and minus 4, right? And then we say again, okay, possible rational zeros, possible rational zeros. Fraction here factors of the last term, minus 4. Here on the denominator, factors of positive 2, right? 2. For you again to make the connection here, the last term over here on the top, this leading coefficient on the bottom here. Now let's do what I did before, right? What are the factors of negative 4? Well, start always with plus minus 1, because 1 is factor of any number, right? But the next 2 is a factor of 4, minus 4, so plus minus 2, right? The next factor. What about 3? Is 3 a factor of 4? Well, 3 doesn't go into 4 evenly, right? 3 doesn't go, so don't put 3 here. Before it was, but not here. What about 4? 4 goes into 4, yes, once, right? So it should be plus minus 4. It starts with plus minus 1, ends with the number itself, plus minus 4, right? Yeah, very good. Now factors of 2. Factors of 2 start with plus minus 1 as usual, right? And what about 2? 2 goes into 2 this time, so it's a factor of 2, right? So plus minus 2. Great. Now, in order to list all the factors, just do these divisions, right? 1 into 1 is 1, so this should be plus minus 1, comma. 1 into 2 now. 1 into 2 is just 2, right? So plus minus 2. 1 into 4. 1 into 4 is just 4 plus minus 4, right? Great. This is what I got, dividing 1 into each of the numbers above. But now we're going to do the same with this other guy. This into this. 2 into 1. 2 into 1 is 1/2, right? But we're going to consider both, the positive and the negative factor, plus minus 1/2, okay? Now, 2 into 2 is 1. The next should be plus minus 1, right? But I already have plus minus 1 here, so I don't have to write it again, okay? Don't write again stuff that is repeated, so it's already there. What about 2 into 4? 2 into 4 is 2, plus minus 2, but I already have plus minus 2, right? So then I don't have to write it again. It means that we are done. Now, for the purpose of the presentation of this list, right, especially when you are looking for this among the multiple choices. Mathematicians have this agreement, kind of the in absolute value, right? The one that is the smallest in absolute value, regardless of the sign. This is 1/2, right? So they like to write this first, plus minus 1/2, followed by the next, that is the smallest in absolute value, 1, plus minus 1. Next, plus minus 2. And finally, plus minus 4. This is the way in which you will find this list on the multiple choices, okay? All right, guys, let's practice. Practice makes the master, right? So let's practice. You will see that it's not really difficult, this application of this theorem. Let's start with number 1. Can you try number 1? This one here. Make it bigger for you to see. They are asking you to figure out what are the possible rational zeros of this polynomial function. I'm going to write it big for you here. X to the 5th minus 4x to the 2nd plus 2x plus 3. And as a hint, I'm going to tell you this: factors of the possible rational zeros will be given by the factors of this on the top, right? And factors of this on the bottom. Professor, there is nothing there. Well, if there is nothing, there's a 1, right? Invisible 1. So figure out all possible divisions of plus 3 here. And this one is an invisible 1 here. Plus 1 if you prefer, right? It's the same. Maybe we should remove the signs. 3 and 1. Yeah. Yeah, write them out as a list here, as a list, and then get them all. Go ahead. And figure out the answer. There is an invisible 1 here. Okay, so let's do it together, okay? So we can go over more examples. Factors of 3. What are factors of 3? Well, we look at, start with plus minus 1, right? Plus minus 1 for a factor of 3. Then the next factor of 3 should be plus minus 3, right? Because plus minus 2 is not a factor of 3. So these are the factors of 3 in the top. On the bottom, factors of 1. Factors of 1, just plus minus 1, right? And then you do this division. Plus minus 1 into plus minus 1, comma, plus minus 1 into plus minus 3, okay? These are the two factors, right? Then when divided by 1, the same. So this should be the list, the final list, right? So we're talking about this guy. Follow, guys? Very good, very good. Try to now, this one is a little bit more challenging, but I think you should be okay with it. This one, number 4. Try number 4. Yeah, very good, very good. Try number 4. I'm gonna give you a hint as usual. Here, possible rational zero, right? Fractional zero, right? Equal this division, right? Factors of the last number, right? Remember this guy was here, divided by factors of this leading term, which happens to be this guy, right? Yeah, this goes here. Yeah, great, great. So 8, -2. And then do the division. The ones on the bottom into the ones on the top in all possible ways, and then you should get your answer, right? Yeah, and after this, we will talk about the fundamental theorem of algebra. Okay, guys, so let's do it together then, okay? So we can move further. For this number 4, if you consider the factors of the number 8, those are, start with plus minus 1, right? Which is a factor of any whole number, right? Then check with 2. 2 goes into 8 evenly, so also plus minus 2, right? Should be the next. 3 doesn't go into 8 evenly, so don't write 3 here. 4 does. 4 goes evenly into 8, so plus minus 4 here. Then 5 doesn't go into 8. 6 doesn't go into 8 evenly, right? 7 doesn't go into 8. 8 is the last one, the last factor, right? Plus minus 8. Over here, factors of -2. Start with plus minus 1 that goes into everything, right? Then the next should be plus minus 2, right? Plus minus 2 goes into this guy, plus minus 2. All right, what is left is to do this division. 1 plus minus 1 into plus minus 1 is just plus minus 1, right? Good. 1 into plus minus 2. 1 into 2 is 2, plus minus 2 this. 1 into 4 is just 4, so plus minus 4 here. 1 into 8 plus minus 8, right? 1 as a divisor is nice, doesn't change these numbers up there, right? But this one, we gotta be careful with this. So let's use a different color. So what about plus minus 2 into 1 now? Plus minus 2 into 1 is gonna give me this guy, plus and minus 1/2, right? Because it's 2 into 1, 1/2, right? Next. Plus minus 2 into 2. 2 into 2 is 1. So it's going to be plus minus 1, but that plus minus 1 is already here, right? I don't have to write it again. It's already there. 2 into 4. 2 into 4 is 2, plus minus 2. It is already written here, right? So I don't have to write again. 2 into 8 is plus minus 4, which is already here as well. So that's it. This is my whole list, right? Now remember, mathematicians, write this considering first the one with the smallest absolute values, 1/2 plus minus, then followed by the next, that is the smallest in absolute value is 1, the next 2, right, plus minus 2, the next plus minus 4, and finally plus minus 8, the last one, right, plus minus 8. So that's it. And this is showing that the answer should be this guy, right, written in this order. Very good, guys. So this is when it comes to figure out the possible rational zeros. Okay, next, let's talk about the fundamental theorem of algebra, right? And then I will cover a lot of examples, guys, for you to have a good background for your homework. and for your exam number 2 that is coming up. The fundamental theorem of algebra. What does it say? It says that if f of x is a polynomial of degree greater than 1, could be a quadratic polynomial, cubic polynomial, polynomial degree 4, or so on, right? Then f of x has exactly n roots. This word may be new for you. Roots means just zeros. It means zeros, right? Zeros. That's what it means. It's just that mathematicians, instead of the word zero, they use roots because this word zero can be confused with the number zero, right? So instead they use the word roots. All right, so the theorem says that a polynomial degree n should have exactly n roots, including multiple and complex roots, right? So including multiplicity and complex numbers that could be some roots of this polynomial. In total, the polynomial should have exactly n roots, which is equivalent to say that we can always factor a polynomial in this form: x minus r1, r1 being one root, x minus r2, r2 being the second root, and so on until x minus rn, rn being the nth root, right? The last root. And some constant might appear up front, but remember, these constants do not determine the zero, right? I show you. Just these guys, right? The opposite of these guys. So this full factorization is always possible for any polynomial when you work with complex numbers, right? So now some solutions may be repeated, right? So what is safe to say is that at most we will get n solutions at most, right? Because some of them might be repeated. But if you consider multiplicity, you should get n roots. Okay. So let me give you an example for you to see how this theorem will help us to find all the solutions, not just the rational zeros, but all the zeros of a polynomial. Okay. So for example, suppose they say find all the zeros of this cubic polynomial, x cubed minus 2x squared plus x minus 2. Solution. Well, I am going to start by sort of guessing what should be the possible rational zeros. Rational zeros. Let's see. I have a theorem that's going to help me to determine that. The theorem says that the possible rational zeros are determined by this last number, which is the constant term, and this first number, which is the leading coefficient, right? The coefficient, constant coefficient, leading coefficient. So these are going to be factors of the number -2 divided by factors of the number, there is an invisible one there, right? 1. Let's do that. But now, what are the factors of -2? Well, we start with plus minus 1. Plus minus 1 is factor of any integer number, right? So next factor, 2. 2 goes even into 2. So plus minus 2 should be another factor. On the denominator, I have just 1. So factors of 1, only plus minus 1, right? Plus minus 1. Now guys, divide that plus minus 1 into plus minus 1. You're going to get here plus minus 1. Plus minus 1 into plus minus 2. You're going to get plus minus 2, right? So in total, I have 1 minus 1, 2 minus 2. 4 candidates, right? 4 possible zeros. So the idea is to start testing them using synthetic division. How are we going to test them? This way. This is the polynomial 1 minus 2, 1 minus 2, right? Coefficients wise. In the corner, you're going to start with -1. Maybe I should write here, right, between parentheses, candidates to test. I'm going to start with -1, then I will test +1, then I will test -2, and finally I will test +2, right? Yeah. If needed, right? Sometimes if I test a couple, I will stop. You will see. All right, starting with -1. Is -1 a solution? Let's see. Bring down 1. 1 times -1, -1. Add -2 plus -1 is -3. -3 times -1 is +3. Add 1 plus 3 is 4. 4 times -1, -4. Adding -4 plus -2, that's -6. Not 0, right? Not 0. Which means that this is not a good one. It's not a solution, right? It's not a 0. So this you just neglect. You said this one, no. Right? And you go ahead with the next test. The next test, go in order, kind of, right? To do this efficiently. I'm gonna test +1 now. +1 here. Again, I write the coefficients of my polynomial. 1 comes down as it is. 1 times 1, 1. Add -2 plus 1, -1. -1 times 1, -1. Adding these two, 1 plus -1 is 0. 0 times 1, 0. Add -2 plus 0, that is -2, right? Again, not 0, which means that this guy is not a solution. So I just cross it out. No, no good. Go with the next, -2, and then 2, right? All right, so with -2, let's see if it works, right? Eventually, it might work, right? So let's just be patient there. 1 -2, 1 -2, and we're gonna test -2, right? 1 comes down, 1 times -2, -2, adding these two, -4, -4 times -2, +8, right? +8. This is 9 here, right? 9 times -18 doesn't work, right? -20, no, no good. But now finally with 2, you will see that that is going to work. You will see. I try to go in order again because that way we kind of are efficient, right? Not 0, right? Not 0. So with 1, here 1 with 2, right? So with 2, 1 times 2 is 2. This is going to be 0. 0 times 2, 0. Adding, this is 1. 1 times 2, 2. 2 plus -2, 0, right? Great. This works, right? This was not 0, but this is 0, right? It works. Then 2 is a solution, right? We found out using this theorem and testing with synthetic division, right? Now, since 2 is a 0, then we can say that f of x from this division, right? Since the quotient here, quotient is this 1 x squared plus 0x plus 1, we can say that f of x will be that quotient, x squared, 0 here is nothing, right? Plus 1 times the divisor, right? The divisor, but what's the divisor? X minus 2. Notice how I am considering the opposite here, right? Opposite. To go from this corner to the factorization, right? Yeah, great. So this is the full factorization, right? Full factorization of the polynomial. But now I have to show or have to find the solutions of this, right? So for that, I have to set my polynomial function equal to 0, which is equivalent to set x squared plus 1 times x minus 2 equal to 0, right? Now set each factor equal to 0 from the full factorization, right? Professor, why do you factor this? This cannot be factored, right? x squared minus 1 is the one that you can factor as x minus 1 times x plus 1, but x squared plus 1 is not factorable, so that is why I left it alone. I set it equal to 0, right? And this should give me the two solutions. So x squared equal -1. Then x equal plus minus the square root of this -1. But the square root of -1, we saw when we did complex numbers, is just I, right? I. So plus minus I here for these two solutions, right? X equal I, one solution, x equal minus I, another solution. So one solution, another solution. From here, plus 2 tells me that x equal 2 is the third solution, right? So 1, 2, 3 solutions, 3 solutions. Conclusion here, the zeros of f of x are, you can list it any way you want, right? Separated by commas, minus I, in any order, right? And 2. Right? 3 solutions. Pay attention to the factor form. Is this in some exercises they might ask you to do this, to show this factor form, right? Solutions, factor form. Okay. And that is how you find the solutions, right? Let me show you another one, another example. This is going to be from our worksheets. In our worksheet, in exercise 1, they show this. Let me show you, explain to you, and then we will go together over exercises, okay? This is special because this polynomial notice is not complete. So it says find all zeros of this polynomial f of x equal x cubed minus 12x minus 6. Find all zeros. Notice here f of x is not complete. It does not have the x squared term, right? So let's complete it by writing our f of x as this. F of x, well, this in the bottom, they leave me space to that. I can write it as this. X cubed minus or plus, doesn't matter, 0x squared, the term was missing, the quadratic term, right? Minus 12x minus 16, right? Minus 16. This way, the polynomial is complete, right? This is complete. It's a complete polynomial. I can work with this, right? To do my synthetic division. All right. So now the next step is to guess what are the possible rational zeros, right? To start with something. So I pay attention to the last number that appears here is called the constant term, or the constant coefficient also. And I pay attention to the first number that appears here is called the leading coefficient, right? This is a number 1. Nothing there means invisible 1. So I gotta pay attention to factors of -16, factors of 1. Factors of -16 are plus and minus 1, but we'll write it next. So this is right here, factors of -16 first, divided by factors of 1, right? Factors of 1. But what is this? What is this? Well, this is going to be equal to factors of -16, a lot of factors of -16, plus minus 1, plus minus 2, plus minus 4. 3 doesn't go even into 16, 5 doesn't go even into 16, 6 doesn't, 7 doesn't, plus minus 8, plus minus 16 is the last number that goes even into 16. Great, these are the factors of -16, factors of 1, plus minus 1. Now divide this plus minus 1 into each of these numbers above. And since 1 is one of the nicest divisors, it doesn't change really the value of these guys, right? So this will be plus minus 1, which is 1 into 1. 1 into 2, plus minus 2, plus minus 4, plus minus 8, plus minus 16. We have a lot of candidates, right, to test, but again, go in order. So once you get your 0, you stop there. You don't have to test them all, right? Yeah, so let's do this in order. So let's say start with plus and minus 1. We can start with 1 or with minus 1, doesn't matter. So start, say, with 1. Right on the top here, the coefficients of your completed polynomial, 1, 0, minus 12, and minus 16. Okay, 1, 0, minus 12, and minus 16 here. And let's test if this guy is a 0. Bring down 1, 1 times 1, 1, add, this is 1. 1 times 1, 1, add, this is minus 11. Minus 11 times 1, minus 11, add, this sum is minus 27. Not 0, right? Not 0. This means just that this guy is not a good one. That's all it means. So go ahead and test the next. What about negative 1? Negative 1. Negative 1 here. Okay, so again, 1, 0, negative 12, negative 16. We write here negative 1, 1 here, negative 1 here, adding negative 1, negative 1 times negative 1, 1, adding negative 11, negative 11 times negative 1, positive 11. Again, the sum is just negative 5, not 0, which means that this guy was not a good one, right? So let's remove them from the list. So this didn't work. Let's try with negative 2 now and 2. So this 1, 0, negative 12, negative 16. Let's try with negative 2. 1 coming down, 1 times negative 2, negative 2, adding these two, negative 2, negative 2 times negative 2, positive 4, adding negative 8. Aha, negative 8 times negative 2, 16, right? 16. Adding these two, 0. Aha, this one good. So this one is a good one, right? So you stop there because you may not need the others, right? Just stop there. Don't worry, I will show you how. So this means that f of x, since the quotient is equal to this, 1x squared minus twice x. I'm picking up the coefficients, right, of my quotient from here, minus 8. Then it means that f of x will factor as the quotient, right, which is this, times the divisor. But what was the divisor? Notice x. What do I write here? Opposite of this, right? Opposite. Opposite. So plus 2. Plus 2. Aha. Now I can factor this, right? As this. This one is factorable, I think, right? I need two numbers whose multiplication is negative 8, whose sum is negative 2. Those two numbers after some trial and error are 4 and 2, right? I want the sum to be negative 2, so the dominant in value has to be this, minus 4 this, plus 2 this, right? Full factorization, right? Which is good. When you have the full factorization set, your f of x equal to 0, which is completely equivalent to set this in factor form equal to 0, right? And from here, we can pick up our solutions quickly. But before we do that, right, I want to say something. I will show you. This is x plus 2 equals 0, x minus 4 equals 0, x plus 2 equals 0, right? Subtracting 2 in both sides, x equal negative 2, one solution. Adding 4 to both sides, x equal 4, another solution. And subtracting 2 in both sides, x equal minus 2, another solution. 3 solutions, but one of them is repeated, right? One of them is repeated. So mathematicians don't like to write repetitions. So you could write this as follows, right? Negative 2, 4, negative 2, right? But instead of writing this, it is better to do this. First, the factorization that you see here, write it this way. x plus 2 is squared, right? X plus 2 times x plus 2, x plus 2 squared, right? Times x minus 4. This is a better representation for the factorization, right? Right? And from here, the factorization, right? This is f of x. Instead of repeating your solutions, right? Just write them once. This is f of x. Let me write it nicely because it's important. F of x here. So f of x, we're saying is this, right? In factor form, simplify. And for this guy, write instead this, -2, 4, right? And you can write a note, say -2 with multiplicity 2, because appears twice, right? Twice. And the exponent on the factor that gave us this solution will tell you that. Very good. And I'm telling you this, guys, because you have to identify using this trick the solutions, right? So better. Yeah. All right. So let's go over the exercises for you to see how they look like. Let's pick, for example, exercise. Let's start with something. This one we did, right? This was done in our notes. I just did it, right? So remember, since we said that this is the multiplicity for -2, multiplicity 2, and we wrote the factorization that way, then the solution should be this, right? This one. You can see it, guys? This, look, -2 with multiplicity 2. The other root was 4, the other 0, and the factorization f of x, x plus 2 squared times x minus 2, right? You see it? Yeah, very good. Now, let's do another one. For example, let's do this one. I'm going to show you some tricks there for you to figure this out quickly. Suppose they ask you to do this. Okay, I'm going to show this to you, and then probably I will ask you to do some other, okay? They say find all zeros, right? Find all solutions or all zeros. Yeah. Yeah, find all zeros. Okay, it's a polynomial degree 4, right? Degree 4. So quickly start by guessing your possible rational solutions. So you're gonna start by considering this fraction, right? The factors of -8 on the top, factors of -1 on the bottom. Factors of -8 are plus, -1, plus, -2, plus, -4, plus, -8, right? Factors of 1, plus, -1. So divide this guy into this, into this, into this, into this, and get the list of your candidates, right, for your rational solutions. Plus, -1, 1 into this, plus, -2, 1 into 4, plus, -4, 1 into 8, plus, -8. Great. So this, we gotta test these guys, right? But be efficient, start with 1, right? 1. What if it works? Then you stop right away, probably, right? Yeah, 1, 6, 7, -6, -8, right? These are the coefficients, starting with 1. 1 down here, 1 times 1, 1. 1 plus 6, 7. 7 times 1, 7. This is 14. 14 times 1, 14. -6, 8. Aha, 8 times 1, 8. I got it at the first try, right? Good, worked. Now, this is the thing, right? This worked. This means that this is a factor, right? X minus 1. So this is telling us that our polynomial, right? This guy, f of x, then x to the 4, right? Just this whole thing, right? can be written since the quotient is 1x to the third. Notice it's x to the third because it's a polynomial of degree 4, right? 7x squared plus 14x plus 8. This guy can be written as this, right? X cubed plus 7x squared plus 14x plus 8 times x minus 1. Remember the relationship between this number in the corner and the number that appears on the factorization? Minus 1 there, right? Minus 1. X minus 1. But now this is a polynomial of degree 3. It's not easy to factor this, right? So again, go and check or test with synthetic division, right? 14, 8. And again, I have 1 and 8 here. So should be the same candidates, right? So if I put 1, since this is being added up, it will never happen, right? Use instead minus 1. Let's test with minus 1. Minus 1 here, this is 6. Minus 6, I have 8. 8 times minus 1, negative 8. Again, I got it at the first try. 0 here, which means that this is a divisor, right? Very good. So this means that your polynomial can be written this way. This is the new quotient, right? The new quotient will be 1x squared plus 6x plus 8, right? So it will write here, x squared plus 6x plus 8 times the divisor, which is x plus 1. I'm writing the opposite of this here, but there was another divisor before, right? So x minus 1 from here. And now factoring this shouldn't be a problem, right? Because in previous courses, they show you how to factor this, right? X here, x here, x plus 1, x minus 1. Now I need two numbers whose multiplication is 8, whose sum is 6. After some trial and error, you will discover those numbers are 2 and 4. So plus 2 here, plus 4 here. Full factorization, look, full factorization, right? And then just set f of x equal to 0, right? And you should get all your solutions from there, okay? This time, all the solutions are real numbers, right? But you know what happens when they are not, right? You have to go after complex numbers for your solutions, right? So this one, by setting each equal to 0, I shouldn't have a problem getting the solutions. From here, subtracting 2 in both sides, x equal minus 2 first solution. From here, subtracting 4 in both sides, x equal minus 4 second solution. From here, x equal negative 1 third solution. And from here, x equal 1 fourth solution, right? The fourth solution. So for number 2, then the solutions and the factorization, which is here, right, showed us that the solution is here. This one, right? Solutions are minus 4, minus 2, minus 1, and 1, as is stated here, right? Minus 2, minus 4, minus 1, and 1. And the factorization is x plus 4, x plus 2 times x plus 1 times x minus 1, right? Opposite to the numbers that appear here. Very good. Very good, guys. All right. So this was done. Now, probably to finish, I should show you this one, right? Sometimes the students ask me, Professor, what happens if there are too many polynomials to test? What should we do? Well, guys, try to be smart, right? Look, for example, in this case, they are asking us to figure out the solutions for this. The numbers are big, right? When you do your guess for the possible rational solution, right? Rational zeros. You gotta deal with the divisors of, or factors, right? Factors of 250, and on the bottom, factors of 1, this invisible 1, right? Notice the polynomial in complete form should be this, right? 0x squared minus 75x minus 20, right? Completing the polynomial. The square term was missing. But now, if you get the divisors of this guy, they're going to be a lot of them, right? Plus minus 5, plus minus 25, plus minus 10, even before, right? A lot of divisors there. So sometimes it's better to do this. I will show you. Plus minus 1. There are a lot of divisors, right? Plus minus 1, plus minus 5, plus minus 10, plus minus 25 will be there, right? A lot of divisors, right? Yeah, but one thing you can do is this. You can start with 1 and 5. 1 is not here, right? You can see it's not listed as the solution. So 5 and 10 are listed. So you should start with these 2. Okay. So again, guys, try to be clever because 1 is not there. So 1 is not going to make it, but these 2, right? These 2 are there. So try with these 2, 5, positive and negative, and positive and negative 10. So let's try with that. So if we test the solutions here, right? 1, 0, don't forget about this 0, right? Minus 75 to minus 25. If I test, let's say 5, 1 here, 5 here, 5 plus 0, 5, 5 times 5, 25, 25 plus negative 75 is minus 50. This is now gonna make it 0, right? Minus 250 here. No, didn't work. So this one is not 0, right? Not 0. So it just means that this is not good, but probably with negative, it may work, right? So let's see, 1, 0, minus 75, minus 25, minus 5. So 1 minus 5 here, minus 5, 25, minus 50, didn't work neither, minus 250, right? Let's try 10, right? 10 for number 4. Yeah. Yeah, minus 5. Let's do it carefully, guys. So this is 25. This is 50, right? Yeah, this was not, this was minus 500, but here, this is good. Because look, this is minus 250, the last one. And when you multiply negative times negative is positive, right? Positive. So this is 0. This is definitely 0. So this is a good one. A good one. All right, so then you go ahead and say, okay, this is the quotient, right? The quotient should be 1x squared minus 5x minus 50, right? So we can say that the polynomial can be factored as this, x squared minus 5x minus 50 times the divisor x plus 5, right? Opposite of this here. Factor further, x here, 2 numbers with multiplication is 50, negative, sum is negative 5. After some trial and error, you will see that this is 10 and 5. Negative here, positive here, right? The sum minus 5, and this x plus 5. But remember how mathematicians represent this. This is the same as this, right? So they just write x plus 5 is squared, and this x minus 10. So now, when you set this equal to 0, the f of x, to find your solutions, right? You're gonna see, guys, this. X plus 5 squared equals 0, x minus 10 equals 0. Taking a square root, x plus 5 equals 0, subtracting 5 in both sides, x equal minus 5. First solution, right? With multiplicity 2, because appears twice, right? In the factorization. And from here, this with multiplicity 1, but remember when the zero, the root has multiplicity 1, you don't say it, right? You say just this solution. So solution will be x equal -5 with multiplicity 2, x equal 10, and the factorization is this, right? Factorization. This is the factorization. So you're going to look for the factorization and the zeros stating its multiplicity if the multiplicity is different than 1, right? So looking back in number 4, then you will see here, guys, that -5 is a solution with multiplicity 2. The other solution is 10. You don't have to write the multiplicity, right? You follow? You don't have to write the multiplicity. It's just 10. -5 with multiplicity 2 is here. Multiplicity 2, 10, 10. And the factorization of this polynomial is just this. X plus 5 squared times x minus 10, right? You see it? So therefore, the solution should be this, right? Yeah, I know, guys, a lot of algebra there, but again, try to be clever, try to test the solutions that appear there in the multiple choice, right? Because there's a lot of divisors that you may encounter here, right? But just start with one, and or if since I didn't see one here, I didn't test this one. I know it's not going to work. I went straight with plus minus 5 because of this, right? And then it worked, right, for this. And then quickly I got my factorization, right? I didn't have to do it twice because the degree of the polynomial was 3, right? If the degree of the polynomial is 4, I show you like in before here, right? You may have to do this process twice, right? Until the degree of this polynomial becomes 2. Once the degree is 2, is a quadratic polynomial, it's easy to factor, right? But the cubic polynomial is not so easy to factor. That is the reason we did this twice here. Try to remember these hints for your homework, guys.